look at the errors that we can encounter in hypothesis testing. Hypothesis testing is not foolproof, or 100% correct all the time. Sometimes, the test can lead us to the wrong conclusions. There are two possible errors in hypothesis testing. They are type 1 error, and type 2 error. In type 1 error, the null hypothesis is actually true, and we should have accepted it. However, the test statistic tells us to reject the null hypothesis instead. In type 2 error, the null hypothesis is actually false, and we should have rejected it. In this case, the test statistic tells us to accept the null hypothesis, again, a wrong conclusion. The following is the confusion matrix showing the truth of the null hypothesis, and the conclusions from the hypothesis test. Of course, in real life, we will never know whether the null hypothesis is actually true or false, unless we study the entire population. Let's assume that the null hypothesis is true. If the test statistic tells us to accept the null hypothesis, then this is a correct conclusion. The probability of making this correct conclusion is 1 minus the level of significance. 1 minus alpha is C, which is the level of confidence. However, if the null hypothesis is true, but the test statistic tells us to reject the null hypothesis, then this is a wrong conclusion. This is a type 1 error, that is, null hypothesis is true, but conclusion is reject null hypothesis. The probability of committing this type 1 error is equal to alpha, the level of significance. We will see how these probabilities come about in the next slide. Let now assume that the null hypothesis is false. If the test statistic tells us to accept the null hypothesis, then this is again a wrong conclusion. This is a type 2 error. That is, null hypothesis is false, but conclusion is accept null hypothesis. The probability of committing this type 2 error is equal to beta. However, if the null hypothesis is false, but the test statistic tells us to reject the null hypothesis, then this is a correct conclusion. The probability of making this correct conclusion is 1 minus beta. And 1 minus beta is called the power of the test. The common power to use is 80%, giving a beta of 20%. Now we look into the details of type 1 error. Given the null hypothesis is true, we should accept the null hypothesis. And the probability of making this correct conclusion is 1 minus alpha, which is the level of confidence. The probability of rejecting the null hypothesis, which is a wrong conclusion, or the probability of committing a type 1 error, is alpha. Why is this so? We look at the example of a two-tailed test we described earlier. The null hypothesis states that the mean weight of adults has not changed, and is still 70 kg. The alternate hypothesis states that the mean weight of adults has changed, and is not equal to 70 kg anymore. In hypothesis testing, we always assume the null hypothesis is true, that is, the mean weight of adults is 70 kg. Let us look at a case where the null hypothesis is really true, that is the mean weight of adults is still 70 kg, and has not changed. The sample mean of a sample drawn from this population is likely to lie within ±3 standard errors, from the mean of 70 kg, 99.7% of the times. The level of significance, alpha, we have chosen for the test is divided into two tails, the right tail and the left tail, with an area of alpha over 2 on each tail. This point is the x-bar critical left and the x-bar critical right. The area between the two tails is 1 minus alpha, or C, which is the level of confidence. We know that we would accept the null hypothesis if the sample mean of the sample drawn from the population lies between the two tails. When we make this conclusion to accept the null hypothesis, given the null hypothesis is true, we have made a correct conclusion. The probability that the sample mean would lie between the two tails is 1 minus alpha, or C, the level of confidence. This represents the probability of making this correct conclusion, 1 minus alpha, which is the level of confidence, C. We also know that we would reject the null hypothesis if the sample mean is less than or equal to x-bar critical left, or greater than or equal to x-bar critical right. Given that the null hypothesis is true, that is, the mean is still 70 kg, this would be a wrong conclusion, a type 1 error. The probability that the sample mean would lie within the two tails is alpha. Therefore, the probability of committing a type 1 error, or the probability of rejecting the null hypothesis, when the null hypothesis is true, is alpha. Now we look into the details of type 2 error. Given the null hypothesis is false, that is, the mean weight of adults now is no longer at 70 kg. The mean weight of adult now has changed to μA. And the difference between 70 kg and μA is large. Given that mean of adult now is at μA, the sample mean of a sample, drawn from this population, is likely to lie within ±3 standard errors from μA, 99.7% of the times. However, we still make conclusion based on the assumption that the null hypothesis is true. That is, we will accept the null hypothesis if the sample mean of the sample, drawn from the population, falls between the two critical regions. Otherwise, we would reject the null hypothesis. As you can see from the graph, if the difference between 70 kg and μA is large enough, the sample mean of a sample, drawn from a population with mean equal to μA, would always fall inside the reject null hypothesis region. The conclusion would always be reject null hypothesis, the correct conclusion. It is very unlikely for the sample mean to fall inside the accept null hypothesis region. Hence, the probability of a type 2 error, beta, is almost zero. Type 2 error is accepting the null hypothesis, when the null hypothesis is false. The power of this test is 1 minus beta, and is almost 100%. There is no chance of committing a type 2 error, when the difference between the hypothesized mean, 70 kg, and the true mean, μA, is large. Again, given the null hypothesis is false, the mean is not 70 kg. The mean is at μA, but the difference between 70 kg and μA is small. Similarly, the sample mean of a sample drawn from this population is likely to lie between μA ±3 standard errors, 99.7% of the times. In this case, we can see there are overlap between 70 ±3 standard errors, and μA ±3 standard errors. Again, we make conclusion based on the assumption that the null hypothesis is true. We would accept the null hypothesis if the sample mean falls between the two critical regions. Otherwise, we would reject the null hypothesis. We will reject the null hypothesis if the sample mean falls inside this reject null hypothesis region. This is a correct conclusion, because we are given that the null hypothesis is false, and we have rejected the null hypothesis. This area shaded in blue represents the probability of making the correct conclusion, and this is the power of the test. We will accept the null hypothesis if the sample mean falls inside this accept null hypothesis region. This is a wrong conclusion, because the null hypothesis is false, and we have accepted the null hypothesis. This is a type 2 error, and is represented by the area shaded in pink. The probability of committing this type 2 error is beta. We can do a few things to increase the power of a test. We can use a one-tailed test instead of a two-tailed test. Instead of dividing alpha into two tails in a two-tailed test, we have the whole of alpha on the right-tailed, and this increases the power of the test, the area shaded in blue. Increase the difference we wish to detect. Finally, increase the sample size. Increasing the sample size would reduce the standard error, thus making the bell curves taller and narrower, and smaller area of overlap. Thank you for watching this presentation.